This is section 15.7 talking about multiplicity that we observe in signals on in an NMR spectrum. Now, we could see a whole variety of peak shapes from singlet, doublet, triplet, quartet, quintet, sextet, septet, and on and on and on. And these are all due to the types of neighbors that a proton has. And the reason why there are different types of shapes is because of the existence of what's called the n+1 neighbor rule. What this says is if a proton has no neighbors, n+1 equals 1, and the peak looks like a singlet. If the proton has one neighbor, n+1 equals 2, and the peak looks like a doublet, and on and on and on. We can talk about the shapes of signals like this. But the reason why is a little complicated mathematically and leads to one of the nicest mathematical relationships, Pascal's triangle, which we'll see in a second. So if you think about one proton and its one neighbor, these really only have two options. One can be up and one can be down, or one can be down and one can be up. So HA looks like a doublet because of these two. But if there are two neighbors, like in this HA with a CH2 neighbor like this, now the two neighboring protons can have down, 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 up, down, or up, up. Because there are 1 to 2 to 1 possibilities, there's a 1 to 2 to 1 relationship with what the peak looks like, or the peak height of each of these three peaks. And that's why two neighbors give a 1 to 2 to 1 triplet like this. We can follow the same exact logic for a quartet or a peak with four, or a signal with four peaks. If A has three neighbors like this, then there will be a lot more options, and there will be a 1 to 3 to 3 to 1 ratio to the possibilities. So because of that, the peak looks like a 1 to 3 to 3 to 1 quartet, as we see here. We can do this on and on until we get to septet, as we saw before, or instead we can look at table 15.3 that shows us our nice Pascal's triangle, where each of these, where the outside of the triangle are all ones, and as the triangle gets bigger, the numbers inside get bigger as well. You can feel free to look up Pascal's triangle if you want to know more about it. There are two major factors that determine whether or not splitting happens. One, are there non-equivalent protons? Equivalent protons don't split each other, but non-equivalent protons do. So in this case, for this C2H2Cl2, this molecule has no splitting between the protons. But they are four protons, and so you would see a signal that equaled four protons there. The second major factor is that splitting is only really observed between 2 or 3 bonds. So what that means is either splitting on the same carbon or splitting on the neighboring carbon or from the neighboring carbon. If you have 2 carbons away, you don't typically see splitting from A to B in this scenario. It's just too far. Now, when the two protons are separated in a vicinal manner, like this, we then talk about the coupling between the two protons. And to talk about the coupling between the two protons, we talk about the coupling constant, or J value, which is measured in hertz. And the J value tells you the number of hertz in between each peak. And the J value is the same, again, no matter what spectrometer you're looking at, but this is another reason why it's very good to have a high megahertz spectrometer or a spectrometer with a strong magnet, because the signals will be much easier to tell apart if you have a strong magnet. Take a look at this 60 megahertz spectrum. You can see that there's one triplet and what looks like there should be a quartet here for this signal corresponding to B. But unfortunately, it looks like one of the signals of that 1 to 3 to 3 to 1 quartet is overlapping with the signal for C in this molecule. However, if we go to a much stronger magnet, a 300 megahertz spectrometer, now the difference is much easier to tell. You still have the triplet and the quartet, but you can see all 4 peaks in the quartet signal, and none of them are overlapping with a signal from C. So having stronger magnets is very, very useful in organic chemistry. So let's look at some patterns that you're likely to see in an NMR spectrometer. First, we're going to see an ethyl groups pattern. In an ethyl group, typically, you'll have a more downfield quartet that corresponds to 2 hydrogens and a more upfield triplet that corresponds to 3 hydrogens. Another signal you're likely to see a lot of is an isopropyl group. In an isopropyl group, you have a more upfield doublet that corresponds to 6 hydrogens and a more downfield septet that corresponds to 1 hydrogen. A tert-butyl group is also often seen, and that is one single peak that has no splitting due to no neighboring protons, because otherwise it would be too far away, and that signal corresponds to 9 hydrogens. So last, let's look at what's called complex splitting. So let's say you're looking at A. If you're looking at proton A, it has only one set of neighbors. That's B. So you would expect the signal for A to be a triplet. But if you're looking at B, you have not only one set of neighbors, which would arise a quartet, but also a set of neighbors to the right, which would be HC, that should give you a triplet. And what you see is not a quartet and a triplet. What you see is a quartet of triplets as shown here. And that's because each individual peak is split in a very complex way, which is why it's called complex splitting. Now, it's difficult to talk about complex splitting because it also depends on the quality of spectrometer that you're using. A much better magnet will be able to show you each of these extra complex splitting patterns, whereas poor magnets will not. Sometimes though, even if you have a very good magnet, it's very difficult to figure out what the precise splitting pattern is, and in organic chemistry, often we call that a multiplet. That essentially just means it's very complex and needs a much, much higher degree of interpretation. So one other thing to note is that sometimes the complex splitting isn't really easy, or not easy. You can't really detect it. It just looks like the signal has too many peaks. For instance, in this 1-nitropropane molecule, the signal corresponding to C is very de-shielded, as we'd expect, and A is very upfield, as we'd expect, but B is in between the two and looks like it should have 1, 2, 3, 4, 5, 6. So that's 6. So n+1 rules tell us that there should be 5. Yeah, there should be 5 neighbors, which is good. But we cannot see the splitting from each. So it looks like it just has 1 neighbor, but in fact it has 2, and we just cannot see the rest of the splitting pattern. So often this is the type of thing you'll see. Instead of complex splitting, it'll just look like the same number of neighbors that it should have. And that is all for section 15.7. Oh, no, it's not. There's actually one small bit. Sorry, I jumped the gun here. So the last bit for section 15.7 is talking about protons that don't have splitting patterns, and those are generally on alcohols or other labile protons. And the reason why this happens is because even though there should be splitting, there could potentially be reactions that change the protons with the solvent. For instance, an alcohol could serve as a base, become an oxonium, and then a water takes the original proton. And all of this could happen much faster than the NMR timescale. And because this happens much faster than the NMR timescale, we don't get accurate splitting for these signals. We just get what looks like a singlet because we are averaging all the potential signals that we could receive. However, if you slow down the rate of proton transfer, then you can in fact see splitting. Another type of proton, a neighboring proton that doesn't produce observable splitting, are aldehydes. These are very downfield signals around 10 ppms, and they typically don't give any splitting because they are physically too far away. So now this is the end of section 15.7.